So let me first introduce myself. So I'm a faculty member of IIT Kanpur. So I work in geometric group theory, and my name is Abhijit. And so this workshop, so this is organized jointly with Professor Tiken Singh of NEHU. So this workshop we earlier planned in 2020 in NEHU, but due to this pandemic, this COVID pandemic, we could not do it. So now we are doing it online. Okay. So I'll given just an overview of this geometric group theory. So what we will get in this workshop. Okay. Yeah. So this workshop, so this is funded by this NCM, and it is organized by this IIT Kanpur and NEHU Shillong. So let me give you a quick overview of this geometric group theory. Okay. So this, so what do you mean? What is the geometric group theory? So this is the branch of mathematics, so that studies finitely generated groups via its action on geometric objects like Euclidean space, hyperbolic space, trees, cat-zero space. Yeah. So so in this workshop, so we'll be dealing with this hyperbolic space, trees. Okay. Yeah. Okay. So let me tell you regarding something about this origin of this geometric group theory. So so it dates back to, I mean, the initial work, it dates back to around the first half of this 20th century. Okay, so by the work of this Den, Nielsen, Van Kampen. So they introduced some topological and geometric ideas into the study of this discrete and study of these discrete groups. Okay, so some of the influential works includes dense algorithm to solve word problems, and this Den-Nielsen theorem to find the mapping class group of this closed surfaces. A precursor of this geometric group theory is the small cancellation theory, and also this Bass series theory. So this small cancellation theory, so it was again introduced by Kreinlinger and further developed by Lydon and Scoop. Okay, so it studies a finitely presented group such that the defining relations have small overlap with each other. And Bass series theory, again, it is introduced by Serre in something about the year 1977. So it derives algebraic information of group acting on simplicial trees. And this emergence of geometric group theory as a distinct area of mathematics, so it came around 1980 to 1990. Okay, so the subject, so this was revolutionized by foundational work of Michel Romer on hyperbolic groups. So what are these hyperbolic groups? So these are the groups whose Cayley graphs are hyperbolic metric spaces. Okay, so you learn about this hyperbolic metric spaces in this workshop. So these hyperbolic metric spaces are very crucial objects in geometric group theory, which captures this negative curvature of a metric space. Okay, so let me first, because this hyperbolic metric space, it is the central object of this geometric group theory. So let me just give you, so what is the origin of this hyperbolic geometry? All right, so most of us know this Euclidean geometry. So Euclidean geometry is based on axioms. Okay, so one of those, this fifth axiom is, so it is also called parallel postulate. So it says that, so given a point and a straight line L in a plane such that this P is not on this line L, so there exists a unique bi-infinite straight line passing through P and not intersecting this L. So the earlier mathematicians, so they thought that so this parallel postulate it can be uh, proved from the remaining axioms. So the earlier axioms from that thing it can be proved, but this attempt continued for around 2000 years until in 19th century, in 1830, Gauss, uh, Ivanovich, Lobachevsky, and John Bolai. So they came up independently with a geometry piloting the parallel postulate of the Euclidean geometry. So this geometry was called to be hyperbolic geometry. So where there exist infinitely many lines through P, passing through P and not intersecting L. Okay, so obviously I have to make sense of this all this thing. So let me give you a model of this hyperbolic geometry. So it is called hyperbolic plane. So you take this upper half plane. So it is the set of all complex numbers as the imaginary part is greater than 0. And instead of taking the Euclidean distance between 2 points, so you define the distance between 2 points in the upper half plane is like this. It is log of mod of z minus w plus z minus w bar divided by mod of z minus w minus z minus w bar. Okay, so one can check that. So the geodesics in this hyperbolic plane are vertical lines and semicircular arcs with centers on real axis. So what do you mean by geodesic? So geodesics are paths of shortest length. Yeah. So now if I so this straight lines now you replace it by geodesics, and the plane you replace it by this this upper half plane. So now if I take a point, so plane I'll refer it to this upper half plane. So now if I take a point P and let us take this geodesic L, which is not intersecting this P. So P is not, L is not passing through this P. So there exist infinitely many geodesics passing through P, which does not intersect this L. Yeah. So this proves that the fifth postulate of this Euclidean geometry, it does not hold. Okay. So now one may ask that why this hyperbolic geometry is interesting. Okay. So so let me ask you this question. So find a simply connected surface of constant curvature. So if I take the Euclidean plane with the Euclidean metric, so the curvature at each point is 0. And if I take the unit sphere, so the curvature at each point is your +1. Okay. And now if I go back to this upper half plane with this hyperbolic distance function, also you can define a Riemannian metric on this upper half plane, which will give you this hyperbolic distance function. So the curvature at each point, so this is -1. So you can compute the curvature. So this will be -1 for this upper half plane. And it cannot be visualized. So this has been proved by Hilbert that this hyperbolic plane, it cannot be isometrically embedded in R3. Okay. So now we have an answer for the simply connected surface of constant curvature. So now what about general surfaces? So can you find a surface of constant curvature? Okay. So if I take just torus, so you can prove that it admits a metric whose curvature at each point is 0. Okay. And if I take a higher genus surface, so let us take g greater than equals to 2 and take a closed orientable surface of genus G. So one can prove that it admits a hyperbolic metric and the curvature at each point is -1. Okay, so this you can obtain as a, so this surface of genus G greater than equals to 2, this you can obtain as a quotient of the upper half plane. Okay, okay. So now let us move to the 3 manifold. So this has been proved by Nisser and Miller. So if I take any closed 3 manifold, means that a manifold without 3 manifold, compact and without boundary. So this can be decomposed as prime manifolds. And so what do you mean by prime manifolds? It has only the decomposition that, so Pi connected sum S3. So it has only this this type of decomposition. Okay. And Thurston, so this is the Thurston generalization conjecture. So he conjectured that so every oriented prime manifold can be further decomposed such that each component administers a geometric structure. Okay, and there are 8 possible geometric structures. So Thurston was awarded Fields Medal for partially solving this conjecture, and fully it was solved by Perelman. Uh, and so this Poincaré conjecture was shown to be a consequence of this. Okay. So let us now move to some notable aspects of this geometric group theory. So, so first one says this quasi-isometric rigidity. So you have to classify finitely generated groups up to quasi-isometric. So given two finitely generated groups, they are quasi-isometric each other to know. So that is a problem. For example, if I take free groups of rank 2 and free groups of rank 3, so they are in fact quasi-isometric to each other. Okay. So the next property, it is called this algorithm property. So it is about the what problem. So what problem says that, so given a finitely generated group or any group, so you have to find an algorithm whether a word represents an identity element or not. And similarly, so the conjugacy problem, it says that, so given two elements, find an algorithm such that they are conjugate to each other or not. And isomorphism problem, again, so given two any groups, so you have to find an algorithm to find whether they are isomorphic to each other or not. So in this workshop, so I think we'll be doing that hyperbolic group. So this has solvable word problem, and also it has solvable conjugacy problem. Okay, and so next is the growth rate of a group. So growth rate, it counts the number of elements of a group that can be written as a product of n generators. So Gromov's well-celebrated theorem, it states that a group of finitely generated group is a virtually nilpotent. So it means that if you take a group of polynomial growth, so it has a finite index subgroup which is nilpotent. Okay. So another type of problems in this geometric group theory is called combination problems. So given a finite collection of groups satisfying a property P, so out of that finite collection, you have to construct a group out of this finite groups satisfying the property P. Okay. So for example, if I take two groups G1 and G2, and suppose they are hyperbolic group, so give some conditions as the amalgamated product of G1 and G2 over the subgroup. So that will be also a hyperbolic. Okay, so this type of problems are called combination problems. Okay. So another aspect is Kleinian groups. So these are discrete subgroups of this PSL2C. And another aspect is you study the boundary at infinity of this hyperbolic group. So these are called Gromov boundaries, and you study maps between the Gromov boundary, and something related to it is called Cannon-Thurston maps. Okay, so Cannon-Thurston maps are so suppose you have two hyperbolic groups such that hyperbolic groups say H and G, H is embedded in G. So Cannon-Thurston maps is the continuous extension of the inclusion of H into G to its Gromov boundary. Okay. So another aspect is mapping class group of surfaces. So this will so the basic part of this mapping class group of surfaces will be covering in this workshop. And another aspect is this outer automorphism groups of free groups. So this will be not doing in this workshop. Yeah, And another thing is relatively hyperbolic proofs. So these are generalizations of this hyperbolic proofs. Again, this has been introduced by Michel Gromov. Uh, so CAD0 spaces and groups acting on K. So CAD0 spaces are again generalizations of this Euclidean space, hyperbolic space. And also, so CAD0 space again, we can't, I think we can't do in this workshop, but we'll be doing something about the small cancellation theory. So it studies group with presentation such that defining relations have small overlap with each other. Okay. So now let us tell about the speakers who will be speaking what. Uh, so Professor Sri Krishna Balaparthi of IIT Guwahati. So he'll be first going through the basic stuffs like his telegraphs, quasi-isometric, and the important thing is here this Swart-Miller lemma. So which says that suppose a group it acts properly discontinuously and co-compactly on a geodesic metric space, then the calligraph of this G is quasi-isometric to that geodesic metric space. Okay, and he'll be introducing this basic hyperbolic geometry, this upper plane, other models of this upper plane, and what are the geodesics and isometries of this this hyperbolic plane. And next, Professor Sip Prasad of IIT Goa. So he'll be speaking on this mapping class groups of surfaces. So what do you mean by hyperbolic surfaces and geodesics in it? And we also dealing with this intersection number of closed curves in surfaces. And I'll be dealing with this hyperbolic metric spaces. And so in hyperbolic metric spaces, geodesic diverge exponentially. So that part I'll be proving. So I'll be also introducing this hyperbolic groups and some of this algorithmic properties. I'll be also saying about this quasi-convex subgroups, and the time is there. So then I'll go to this relatively hyperbolic groups. Okay. So Professor Pranab Sardar of ISR Mohali, so he'll be speaking on this Bastre tree. So his talk will be related to this combination theorems that I told. He'll be also dealing with this graph of groups and its fundamental. And Professor Shobroto Das, so he'll be speaking on the response cancellation theories and isoperimetric inequalities. And Professor Arpan Kaviraj of IIT Palakkad, so he'll be speaking on this curve complex and this finite generation and presentation of this mapping class group of surfaces. He'll be also speaking on diagonal space, and if time is left, I think he'll prove the Stern-Nielsen-Baer theorem. Okay, yeah. So this is about all about this. So what we'll get in this workshop. Okay. So if you have any question, you can ask. So the first lecture will start with Professor Sri Krishna of IIT Guwahati at 9:30.